Without wasting any time on introduction, let's get into the video. First one is the Hilbert's Hotel. Imagine you are traveling to a city and have forgotten to book a room beforehand. Fortunately, you come across a beautiful hotel named after the famous mathematician David Hilbert, whose work you greatly appreciate. You step up to reception and see that the hotel has an infinite number of rooms. The room numbers correspond to the natural numbers 1, 2, 3, 4, without ever coming to an end. The receptionist tells you that the hotel is fully booked, however. But you know your way around math, so you don't let yourself be fobbed off so easily. You know a trick that will allow you, and all the other endless guests, to find a room too. You suggest to the receptionist that each guest move to the room numbered 1 higher than their current lodging. So the person from room 1 goes to room 2, the person from room 2 to room 3, and so on. Because Hilbert's Hotel has an unlimited number of rooms available, even when fully booked, there is still room for more guests. German mathematician David Hilbert presented this supposed paradox during a 1925 lecture on infinity. The next paradox is more familiar to many. When I was at school, it was not uncommon for several of my classmates to have their birthday on the same day. In fact, I also shared a birthday with a classmate. At first, this seems like a huge coincidence. After all, a year has 365 days, and a school class consists of around 20 to 30 students. Our gut feeling therefore tells us that it is unlikely that 2 children were born on the same day. In fact, the probability that 2 people in a group of 23 have a birthday on the same day is more than 50%. To better understand this, it helps to look not at the number of people, but at the number of pairs of people. From 23 people, after doing math, its 253 pairs can be formed, and this number exceeds half of all the days in a year. If we look at the probability that one of the pupils in a school class of 23 was born on a particular date, however, the probability is only 6.1%. The birthday paradox therefore arises from the fact that looking at pairs of students gives you a greater number of possibilities than if you only look at individuals. This fact has tangible effects in cryptography, for example. If you want to sign a digital contract, for example, hash functions are used. If even the smallest change is made to the original document, the hash that is formed from it is completely different. By keeping their hash, the signatory can prove what they originally signed, making the process tamper-proof. There is an extremely low probability that 2 completely different documents will generate one and the same hash, however, and that poses a security risk. As a rule, the length of the hash function is chosen so that such collisions, where 2 different data records produce the same hash, are extremely rare. A hacker can carry out a birthday attack, however. They can generate many different documents and compare their hash functions in pairs, just as a teacher compares the birthdays of classmates instead of focusing on a specific date and a single student. In practice, a birthday attack could look like this. I first create 2 contracts, V1 and V2. V1 is a fair contract, but V2 has wording that is in my favor. Then I change both contracts in various places. I add spaces, tabs, and line breaks to create variations of V1 and V2. These changes are virtually invisible to a reader, but they drastically change the hash function of the documents. If I compare the individual hash functions of the modified contracts, V1 and V2 in pairs, I will find a matching hash much more quickly than if I specifically try to reproduce a particular hash, such as that of V1. If I find a matching pair, I can give you the contract V1 to sign, but claim afterward that you signed V2. Because both generate the same hash, the fraud cannot be detected by digital signature software. Now it's time to dive into the third problem, which is Russell's antinomy. British philosopher Bertrand Russell formulated this paradox in 1901, and it's sometimes called Russell's antinomy, a term for a statement that describes 2 seemingly contradictory ideas. Unlike Hilbert's Hotel and the birthday paradox, Russell's antinomy is not a result that merely eludes our intuition. It contradicts the rules of logic per se. The antinomy produces statements that can be neither false nor true. One famous example of Russell's antinomy is the Barber Paradox. Suppose a barber shaves all the men in town who do not shave themselves, and only those men. Does the barber shave himself? If he shaves himself, then he no longer belongs to the group of people who do not shave themselves. But if he does not shave himself, then, by definition, he would have to shave himself, because all residents who do not shave themselves go to him. This problem arises because of poorly defined sets. The natural numbers, for example, form a set, as does the set of all inhabitants that do not shave themselves. This also allows sets to contain themselves or refer to themselves as a whole, and these properties lead to contradictions. This antinomy led to the end of what mathematicians call naive set theory. The foundation of mathematics continues to rely on set theory. But sets in this construct are no longer mere collections, and instead must fulfill certain conditions. For example, sets must be composed of already existing sets and must not refer to themselves. This rules out antinomies such as the Barber Paradox. To put this in mathematical notation, people in town who can grow a beard and are men form a set M. That set includes the men who shave themselves and those who do not. Next, the set C includes all the barber's customers. To form C, you have to follow the rules of modern set theory. If the barber is a man with a beard or part of M, then the set of customers cannot be defined as all male residents who do not shave themselves, because in this case the definition would refer to itself with both the barber and the customers as part of M. Set theory simply does not permit such a definition. But if the barber is not part of M, for instance, if the barber is a woman or unable to grow a beard, then the definition is permitted. Now let's delve into another intriguing paradox that has puzzled thinkers for centuries: the liar paradox. This paradox is simple in its statement but complex in its implications. It revolves around a single sentence: "This statement is false." At first glance, this sentence seems harmless. If the statement is true, then what it says must hold. According to the statement, it is false. But if it is false, then what it says is not true, which would mean that the statement must be true. This creates an endless loop of contradiction, a paradox. The liar paradox challenges our understanding of truth and falsehood. It was first articulated by the ancient Greek philosopher Epimenides, who was a Cretan. He famously stated, "All Cretans are liars." If Epimenides is telling the truth, then he is lying, which means he is telling the truth, and so on. In the realm of logic, it questions the very nature of truth. How can something be both true and false at the same time? In computer science, similar paradoxes can arise in programming, leading to infinite loops or system crashes. One way to approach the liar paradox is through the lens of formal logic. In this framework, statements must adhere to strict rules to avoid contradictions. For instance, some logical systems introduce a third value, undefined, to account for such paradoxical statements. This way, the statement, "This statement is false," is neither true nor false, but falls into a category that prevents logical inconsistency. The liar paradox also finds its place in popular culture. From complex plots in science fiction to mind-bending episodes in TV shows, it serves as a narrative device that challenges characters and audiences alike to question their perception of reality. In conclusion, all the Paradox X are more than just a logical curiosity. It encourages us to think critically about the nature of truth and to explore the boundaries of logic and reason.